Okay, good afternoon, everyone. I hope you enjoyed lunch, and I'm glad you made it to this talk. I'm going to skip all the introductions and all the pleasantries because we have loads of code to go through, so let's just get on with it. We're going to build this. You might say, oh my God, what's that? Well, I'll have you know it's a React.js application. Anyway, what we're going to do is send tweets with #reactive_summit. And the idea is that you take a picture of either a beer, or a cake, or a salad, or a laptop. Now, the first three are probably out, but at least you have laptops, right? And then I have trained it to recognize 5 really, really important people. We have Helena, we have Jonas Bonner, we have Konrad Malawski, we have James Roper. And if you can manage to tweet either one of these objects or one of these people, then we'll build these scorecards, sort of storyboards, because we're going to recognize what's on the image. We're going to call it beer, salad, cake, whatever. And then we're going to recognize people on that image or on those series of tweets within, I think the window is 30 seconds. And then we'll collect the handles and we'll build a story of what you guys are seeing in front of your phones. Now, I actually completely expect that it's going to get it wrong, right? So this, I think, is a great example of beer. But that will be the fun bit, right? Okay, right. So how did we get there, right? So this is, first of all, the introduction of, we had a system like this that did computer vision, that it did recognition, and it was an absolute mess. Now, I say that now, after years of experience of running this thing, because we started with external APIs, WebSocket APIs, and JavaScript, just plain old REST APIs, and of course mobile apps. And then we pushed the results to someone else's systems. In terms of technologies, we had Cassandra, as everyone would expect. We had Akka and Spray back in the day. And we tied the components together with RabbitMQ. And we had a whole bunch of native code. So that was the old world. And it sort of worked. You sort of go, okay, well, that's not too bad, right? All of this can be made reactive. All of this can be made asynchronous and responsive. Except, well, there were details. And the details were that we had 2 topics. And we had a topic called scene, where we sent the images. And we thought, okay, well, if we push it on that topic, we're going to get back a response that says, this is a cake, a beer, a laptop, or a salad. And we had the identity topic, and it would be the same thing, right? We would push an image on the identity topic, and we would expect to get a response back that says, oh, well, this is clearly Jamie Allen. That sort of business. Now, if anyone's tried to actually use RabbitMQ in Angular, one of the ways to do this is if you want a response in this request-response world, and you can see this is like the first smell. It's not a good way of doing things. But in the request-response world, you'd push a message out on a queue, say a topic, and you would create a temporary queue, and you would expect a response on that temporary queue, and the temporary queue would get deleted after you receive a response. Now, that's a nice way of doing it, of course. This is the equivalent of having a special mailbox. It's like sending a letter. You can take your message, package it up, and include a self-addressed envelope, and you send it somewhere. And then you say, when you're done with the processing, take out the envelope and send it back to me, because it has the address. But of course, it introduces a whole bunch of orchestration code into the Akka code bases here. What made it even worse is that our delivery semantics were less than ideal. So to be completely exact, we had a fire and forget on the send side. Not great, right? We could lose a message. We had at most once delivery on the native components. And on the reverse side, it was, well, the same thing, but in reverse. We had fire and forget on the response, and then we had at most once delivery on the Akka side. But at the same time, we wanted to build a relatively reliable system. So we really didn't want to lose messages. And so we had this massively complicated orchestration code. So it was a big, fat, finite state machines. And you can imagine the number of transitions between the states was growing. And we had to handle all these timeouts. So essentially, all the complexity of guaranteeing message delivery was pushed to Scala code. And this became really, really deeply unpleasant. So what do we do, right? I mean, this is clearly broken, and this view of the system, this is a distributed monolith, right? You haven't actually gained any benefit from microservices. If you look at the stuff that goes on the queues, the payloads that go on the queues, you have no versioning. So you can't actually reason about putting new stuff in, expecting responses in a different format. The only thing that was going on these queues were these maps of string to string headers, and then bytes representing the requests, or rather the payloads, right? So you had array of bytes that represented the image, and on the response side, we got an array of bytes that represented some sort of JSON response. That's pretty terrible, right? What if we wanted to upgrade one of these microservices? Say, introduce version 1.1, 1.2, dare I say version 2? Well, we were stuck. I mean, we could program, right? We could say, oh, well, if version is so-and-so, if a special header has a special value, then something else. That really isn't the right thing to do. Now, as a result of that, right, you're tied into a world where all the components have to be released at the same time. So you think you're getting the benefits of microservices, and to a degree you are, right? I mean, you're getting isolation. So if you look at the native code, which was C++, and my C++ is terrible, even worse than my Scala, which says a lot, and so it would segfault. Well, that's not good, right? Now, okay, well, we have RabbitMQ, and we'll redeliver the message, except when RabbitMQ fails. We have misconfigured it, right? We didn't have durable queues. You think, we should know better now, and we do. So we've improved it. So never mind all that. What else are we going to do? What else are we going to build today? Well, we're going to do proper microservices, and we're going to do microservices that you can actually try out. So we'll have an ingestion module. So we're going to do some Akka streams, ingest these tweets. And then, as it says, right, then I have a React.js. I mean, that was a cool thing to find this logo. So we push stuff out over a WebSocket to a React.js application. That really is the detail. That doesn't matter. I know we're reactive, but never mind all that. So, in terms of technologies, it's the usual setup, right? We have Akka plus Akka HTTP plus Akka persistence plus Akka persistence Cassandra. Then we have Kafka to deal with the messaging. So far, so good. And nothing else, really. This is quite cool, right? We haven't introduced any more complicated stuff. We still have a queue, an actor component, and a database. Now, how do we structure these queues? Well, I mean, if you had a chance to go and see Jako's and Simon's talk yesterday, you'll notice some of the patterns that they talked about. So we have a tweet image topic. So this is where we're going to send the tweet images. Now, everyone's saying, oh, whoa, bytes? What the hell? Didn't you say that that was the wrong idea to do? Don't worry. That's next slide. Okay, so we're going to send some stuff down the tweet image topic. And we then have two consumer groups. Right? So we will partition it because we want to get our parallelism, and we get two consumer groups because we want each message to be delivered to each consumer group. So the vision microservice, the identity microservice sees the bytes that make up the image. The scene microservice sees the bytes that make up the image. They do some magical processing, and then they send one or more, or zero or more messages on the scene topic and on the identity topic. And just so we can see things, we're going to wire in a dashboard service that's going to display the stuff on the React.js application. Okay, so these payloads. Well, this is where it gets slightly more interesting. Of course, we're not sending any old bytes. We need to be able to upgrade things and to reason about things. So it's always useful to define a protocol for your application, for all your microservices. And it's even better to be able to publish this protocol and say, okay, you download this definition of protocol, and then it's possible to build bindings to this protocol in many different languages. So in this particular application, we've chosen protobuf. And so everything that we publish, all the data that goes in and out of our system is expressed in these protobuf message definitions. And then what we can do is at build time in SBT is to generate the case classes that automatically map between the protobuf bytes and instances of these case classes. Now, because we have definition of these messages, we have some reasonable language to describe them, we can immediately publish JSON. It's not a problem. We are restricted to very few types. That's quite good. That maps reasonably well to JSON. And all of a sudden, we have a reliable and stable API for all of our code. Now, if you're doing distributed system, you need to think about monitoring and tracing. Because at some point, something's going to break, and someone is going to say, how far did it get? Where did the message go? And you need to be able to identify it by using some sort of correlation ID or a message ID. And there are some services, not on this diagram, but you might want to be building, say, an auditing service or some sort of metering service. And in that case, you don't necessarily care about the payload, but care about the headers. So the few things I have at the top: version, processing timestamp, ingestion timestamp, correlation ID, message ID, and message type. And then there's the payload, the stuff, the message. So some services need to see the payload, and there are some microservices, like, as I said, auditing and metering and billing, that don't care, right? All they need to see is, we've processed a message. That's all that matters. And now we can turn to what goes down these topics. So on the tweet image topic, the payload is just bytes, but wrapped in the envelope, right? Everything is in an envelope, and the payload on tweet image is bytes, an array of bytes that represents the image. On the topic scene, we have the scene message, right? That's the response. Here is what we found. And on the identity topic, of course, we have the identity response. Nice and easy. Okay, next horrible thing that we got wrong in the old system was delivery semantics. So we're going to explore two things. Fire and forget is easy. At most once on the other end, that's easy. You know, we don't have to care about that. But what's more interesting is at least once on scene and at least once delivery on identity. And there are two variants, and the reason why I have 1 and 2 is because the scene microservice is quick. It will do its processing within the time that is necessary to confirm the records, the offsets back to Kafka. So we don't have to take on extra storage. With the identity service, we do a lot of work, and so the work would take too long for us to confirm it back to Kafka, and so we'd get missed deliveries, and the brokers would try to rebalance the partitions. So we have to do local persistence. We read stuff from Kafka, remember it locally, confirm once we've remembered the stuff locally, and then process the message that we've read. So, well, let's slowly get through it. So, the formats. The numbers, if anyone's never seen, if you haven't seen protobuf yet, hopefully this isn't too alien. So, message, and then we have several types, and the equals are, the positions of the bytes, where the particular bytes that make up the version, processing timestamp, are meant to go in the message format. And so what we say is that we have a 32-bit integer version. So every envelope that you read will say, what version am I? Like 100, 101, 102, 200, and so on. So you can identify what the payload is going to be. You have processing timestamp and ingestion timestamp. So let's tackle the ingestion one. It's the first time we've seen the message. It comes in, we've read it from Twitter. We say, okay, when have we done it? And then each microservice, as the processing goes, right, it will modify it will keep the ingestion timestamp, and it will modify the processing timestamp. So we can then, if we're writing stuff to logs, we can trace the whole message flow and say it took us so much time to process the message through the entire system. We have correlation ID in case we need to fan out things. You might find it useful to include message ID if you want to deduplicate things in a really easy way. You could probably do equals on the whole message, but it might be sufficient to just generate message ID when you see it, and then you can deduplicate. And then finally, message type and payload are linked together because payload is just bytes. Now, protobuf encoded bytes, I'll give you that, but you need to know which thing you're going to get out of it. So it's the message type. Think MIME type loosely. So all these together will then map to scenes. So this is really easy, right? So messages can be embedded. So you can have message scene, like an outer class, if you like, and then inside you can have label, and then we have plain old scalar fields like label, the actual thing that's in it, and a score. Repeated is simply saying an array, a sequence of labels. So if I hold a scene instance, it will have labels as a sequence of scene.label class, and each scene.label will have label and score. I can do discriminated unions. I can do sum types. So one-off face is, in Scala speak, a sealed trait. So one-off face will be either identified face or an unknown face, but never both together. So this will be a sealed trait, and the two case classes that represent the values. Enums and swifts. So if you want to build binding to Swift, this will be an enum with the appropriate values. Identified face has a name and a score, and it doesn't have bold string and bold double, which is terrible, but sorry about that. Now, that's a public API. Each of these microservices may well publish its internal API. Right? So there is stuff that you want to persist in, say, Cassandra, or there is stuff that each microservice might want to send to itself over Kafka. Now, you really don't want to do Java serialization. If you do that, your messages end up this toxic stuff that's going to bite you, because you add a field, you compile with a future version of the Scala compiler or the Java compiler, and it all breaks. So everything that you write anywhere has to be properly described. And I don't particularly care whether you use protobuf or anything else, but use something that you can rely on. Use something that will give you forward and backward compatibility. That's all there is to it. And now we get to more of the meat. So fire and forget is really nice and simple. We get a producer conf, get config, we have a string serializer for the keys, we have a serializer taking an envelope by taking its 2-byte array. So this is essentially a protobuf serializer for the payloads and a string serializer for the keys. When we want to send something, we get the producer. When we want to send something, we do that, right? Producer, we can create a record that has the topic name, tweet image, handle, which is the key, which is a string, which matches our string serializer, and then an envelope, which matches our Kafka serializer of envelope. Nice and easy. What we get from it is a future of record metadata that we promptly forget. And we sort of go, never mind all that. Fire and forget. Okay. At least once delivery. Oh, okay, well, that's sort of interesting. What do we want to do? At least once delivery and processing. In which case, we get the same thing, right? We get records, this mini batch of things that Kafka sent to us. We get all the records. Remember, we've configured the string serializer and the envelope protobuf deserializer. And so what we get is a pairs of keys and these envelopes. We want to send them out, right? I see that makes sense, right? We've done some processing. We've produced this out envelope by doing some magic, and we want to send them out. But we want to only confirm that we've received the message once we've sent them all out. So we have to remember the sequence of future of record metadata. We will flip the containers, so from a sequence of future of record metadata, we're going to get future of sequence of record metadata by doing future.sequence, and on success, we're going to confirm the original message. So if something breaks in our processing, we will have never confirmed it, and so we'll get redelivery from Kafka. That's cool. We won't lose the message. And at the same time, we can do enough processing quickly enough so that Kafka is happy. We confirm in time. Okay, well, what if it's more complicated? What if we have some processing that cannot be done quickly enough to confirm in time? Well, okay, this is slightly more complicated. Well, we need to have persistent actor. We need to have local persistence. Because once we read stuff from Kafka, we have to write it somewhere so that if we crash, we can recover and never forget the message that we've received. All right, we define receive recover as the default behavior. Get to that in just a minute. So this is nearly the same, right? We get the mini batch that we got from Kafka, consumer records, which is a sequence of stuff from the key deserializer and the envelope and the payload deserializer, in our case, a string and an envelope. And we're going to do some processing. We're going to pull out the data that we want from it. Now's the cool stuff, right? So we will persist. Persist meaning akka persistence persist. We will write asynchronously, and that's the key thing. We'll write asynchronously to a journal, like a Cassandra database. And this callback, this result arrow, that happens when we get confirmation from Cassandra that the write has finished. All right, so don't be fooled by persist and persist async. Persist async, both of them are asynchronous. They just differ in the way in which they handle the incoming messages while we're waiting for confirmation from Cassandra. Okay, so what next? What next? So in the handler, right, we've persisted, so we won't forget it. But then we have to guarantee that ourselves within akka persistence, we will have at least once delivery in the local actor system, which is the deliver call. So we need to write a special, essentially, watermark in our journal, in the local journal for this particular actor system, say, how far did we get in our persistent journals? Because if we crash, if we didn't do this at least once delivery with Kafka, if we crashed, we would get every message replayed to us. We sort of don't want that. We can keep a watermark. So that's the purpose of this deliver, which generates a delivery ID, which is monotonously increasing identifier that is essentially a pointer to our offset in the journal that Kafka maintains, akka maintains. Once all that happens, we can reply back to the Kafka producer that, yep, we have it, we can confirm. And then the stuff, the messages that we've sent, this tuple of delivery and identify faces goes to our usual handler, where we can handle it. So we have the business where we send all the messages to Kafka, and on success, we'll confirm delivery. So we'll write a watermark and say, cool, that's it, we've processed it, at least once delivery worked. If we're recovering, which means we're not seeing the tuples, we see just the raw identify faces, the stuff we put into akka persist, we do the same thing, but the difference is that on failure of that, right, we crashed. So why did we crash? Well, maybe the producer is broken. It makes sense to retry, but if we crash again, then we want to send a self-kill message, which triggers the supervision strategy again. And then depending on how we configure our supervision strategy, you might have a fixed number of retries. And if that fails for, say, 10 times, you would kill the parent actor, and that might kill the whole JVM, which in case you're running in a Docker container, in DCOS you would say, oh, wow, this microservice has died. Let me start a new one. And that's exactly the kind of system that you want to build. And let me just go through all these fancy animations again. Yay. At most, once delivery is trivial. I'm not sure if I should even insult your intelligence with it, right? The pointers are for each. We're forgetting stuff. Never mind. Let's just get it, receive it, forget it. And we even put stuff on the local actor system's event bus. No guarantees whatsoever, right? If this dies, message is gone. But we confirm it immediately. We'll just say, oh, we have something. We're going to do our best, but never mind. Okay. Enough. Enough. This was fun, but let's program. Okay, here we go. So let's ingest. So I said that we need to have an ingestion service, which is this guy. So what are we going to do? Well, we have some configuration details from Twitter. So I have a file that I've stashed away that reads environment variables because it wants a consumer key and consumer secret. So I haven't quite shared those with you. You'll have to get your own, but that's easy enough to do. Okay, what do we have to do? Well, we have to get this whole OAuth request. So there's a convenient library that does all that. We'll create an authenticated co-auth request. We'll pull out the value of the authorization header. And then for each of those guys, right, remember these are all futures. So for each of those, we're going to ingest. Okay, well, what are we ingesting? We're going to make this, it's red, but don't worry, that's IntelliJ IDEA. That's not me, it's not you. It's cool. Yeah, I know. So what do we do? Well, a simple like a stream where we construct this post to Twitter, and we say, okay, well, give me the response, this chunked HTTP response to a query that we type in, and the query happens to be #reactive summit. So that's how we know we're doing the right thing. So we're going to track #reactive summit, which means we're going to get all these tweets filtered. They're going to come in here. They're going to be given to us in this stream of bytes that represents the entity, because it's a chunked response, right? So we need to have some sort of marker that delimitates each chunk. We're going to use new line. We'll filter it. We'll map it by parsing it into a simplified tweet format to read the stuff from JSON. And then if that all worked, we're going to send it to the simplified tweet processor actor. Right. What does that do? Not much now. Wow, okay, that's not good. We need to program. First, we need to download the media, right? So the simplified tweet contains all the stuff from the tweet. We don't care about the text. We care about the media URLs. We just have to download them. So it's a simple, relatively simple thing, right? For all the media URLs, a sequence of strings. We're going to construct an HTTP request. We're going to do a get on that media request. We're going to fire up a single request. We're going to consume all the bytes by turning the entity to a strict one. So it's not a stream, it's now an array of bytes. We have the response. And for all of those, so for all the responses, remember these are futures, so for each isn't like for each, it's a for each of the future. So when it finishes, we can do something interesting. We have the data bytes, this array of bytes that make up the image. And we're going to send a tweet image to self. Okay. And in here, remember I promised fire and forget. We'll just take the configured Kafka producer, we'll put it on the tweet image topic, and we're done. Right? So bytes go out. We have all the images ingested, downloaded, we have all the media. It's all asynchronous, all really quite cool, all driven by the configured dispatcher. Really nice, even if I say so. All right. Now you say, okay, where does it go? Well, we need to, let's look at the scene recognition. Okay. So what do we expect? Let's start with this, right? Let's do some proper programming for a second. So let's see, we have a test, and what we expect is for the test to say that this is beer, clearly, right? This is cake. We can all see that. We have the advantage of billions of years of evolution. We have laptop, and we have salad. You know, good Google images. If you know, your mileage may vary. If you take any of these pictures actually with your phone, who knows? But it runs on these, and it runs on many others. Okay, cool. So, all right, hang on. Let's write some code. So, okay. There's some magic stuff here, which we'll get to in just a minute. And then for all scenes, simply iterates over these resources and pulls out the stuff before the .jpeg, and it says, okay, well, let's classify the stream, you know, the bytes that make up this resource. I mean, the code is here, so it's not magic. And then, well, the label should match, and the score should be more than 0.8. Right, not bad. Let's run. Okay, now let's run. Compiling and running. It takes a moment. It needs to load all the network parameters, which is a 13-layer deep. Come back. Ew, that's not good, right? But anyway, 13-layer deep AlexNet. So if anyone's done some ConvNet programming, AlexNet is a published network architecture. I haven't invented it. You know, people who are much smarter than me have implemented it, and I've just taken the shape of the network and I've trained it, which produced all these network parameters that I can load. So 99 megabytes of floating point numbers that make up the network and then the weight and the biases. And so it can now recognize it, except it doesn't. Oh, okay, that's easy, right? Implementation is missing. We still haven't programmed enough. So what we have to do is simply, I say simply, right? But this took a while. But we need to implement this. Like that. right? It's a shame that none of my programming can actually be done with shortcuts predefined. Anyway, we take the image, we treat it as a row vector, and we ask the network for output, and it gives us a vector of predictions, and the vector will have as many elements as there are labels. And the first element of the output, the first number of the output vector will be the probability of the first label being the thing in the image. Second will be, yeah, you get the idea, right? So now we can run it again, and it will be green. I mean, I practiced, so, you sort of expect that. This is work, is not going to work, I don't know. Yeah, of course, right? Excellent, so it makes the right predictions. We can feed it these images, and it all works. Okay, so all we have to do is wire it into our actor. So we have scene classification actor, because remember, we need to receive stuff from Kafka, decode it, pull it out from the envelope, and then do this guaranteed at least once delivery with the right confirmation going back to Kafka. And we need to wire in all this magical image recognition. Okay. How do we do that? Well, okay, let's start with props. So we loaded the scene classifier just as I've done. Now, it would be really unfair if you could clone the code and you saw that. I mean, if you had my machine, if your name is Jan Machacek on it, admit it freely. There's no shame, but I guess I'm the only one, right? So I have included the models in S3, and if you do sbt docker, it downloads the images into your Docker containers and puts them right there. So when you clone the repository after the talk, if you want to have it a go, sbt docker, and then provisioning all the Docker machines up, and you're running with everything ready to go. No thanks, brilliant. Okay, right. Let's continue. So we get our consumer, we get our producer, and we finish with props. Right, this is the usual Akka code now. Okay, typing, but we haven't done anything too adventurous. This is where it gets more interesting. So, okay, let's take a look at this guy. So, we have a consumer actor. So inside this scene classifier actor, we create one actor that connects to Kafka, that will receive the messages from it, will poll. So we'll get some idea of back pressure. We get redelivery from our Kafka client. Now, what do we want to do? Well, just like Simon and Jaco yesterday said, we want to subscribe to a sequence of topics. In our case, just one, tweet image. And we want to subscribe in auto-partitioning mode, because we're lazy, right? We're just going to say, Kafka, you deal with the partitioning of it. You deal with reassigning, rebalancing the consumers to all the partitions. So that's how it's done. Now, what's going to happen is that the Kafka consumer actor is going to send us, now us meaning this actor, because downstream actor is self, it's going to send us payloads that we can extract. Like so. Fantastic, right? So extractor has an unapply method that is wired into the key deserializer and the payload deserializer. And so we get the handle. So handle here. Come on. There you go. Handle is a string. I'm not sure if you can see it, but take my word for it. Handle is a string because it's a string deserializer that we've configured the Kafka consumer with. And envelope here is our envelope, the generated case class for the envelope protocol. Now, it looks ugly, but hey-ho, it's generated code, right? You can format it if you like. But what you need to look at is not this, but it's the protocol definition. That's nice. This is where you write your comments. This is what you publish. The generated code, don't look at it. It's not meant for humans. That's for machines. Okay. All right, never mind. Here we are. So these futures here are a sequence of future of record metadata, right? So what we want to do is to guarantee delivery, like so. So with that future sequence, we turn a sequence of futures into a future of sequences, and then when it all works, we'll confirm back to Kafka. Guaranteed at least once delivery, right? Kafka will take care of it. If one of these guys dies, it will rebalance the partition. It will maintain track of all the consumers. We have selected, the keys to be the handles. So if we want to do some aggregation on the tweets, we are free to do so because of our keying strategy. Excellent. All right. Now let's deal with the more complicated thing, the identity matcher, right? So I've left a whole bunch of code in that, isn't really all that terribly important. So how to create the props. Okay, that's nice and easy. But this is the important stuff. We define the right supervision strategy. You should do that when you do akka programming as a matter of fact, right? That's given. And what we're going to say is, well, we're going to have maximum 10 number of retries within 10 seconds. And whatever exception, whatever caused the failure, we're going to, our supervision strategy is to restart ourselves. And when we exhaust this, it's this actor's supervisor that's going to be told that, one of these children, you failed, now what? And we have a similar supervision strategy. And then, of course, the final supervision strategy is, well, system.exit. And then, DCOS kicks in. Right, what else do we do? Akka persistence, we define the persistence ID. Okay, so far so good, so that these messages will be identified in the journal as going to this actor, right? Journal is this massive table, we just need to say, which messages go to this actor? That's this. Now we have stuff. So who's done OpenCV? No one? No one has tried OpenCV. Have a look, it's brilliant, it's wonderful, it's native code, and it's not thread safe. Naha, you say. Not thread safe. Well, how can I do this, right? So if we weren't in an actor, we'd be in real big trouble. So this method, as an example. Okay, let's see what's in it. Maybe we can make it thread safe. Yeah, good luck. Public native void. Ha, now what? So it is unsafe. There's nothing you can do about it. The underlying implementation is native code. I even happen to have, look. Oh no, maybe it's in a different. No, I don't. I was looking for a crash log, which that's seg fault. It's not there. But anyway, right, you get the idea. It's seg faults, it crashes. So this is where it's actually really important. You can really take advantage of the fact that you're inside an actor. You have some sensible containment of mutable state and of threading. So inside this actor, this stuff happens in one thread. And until it finishes, no other thread will jump into this processing. So you really want that. If you didn't have that, well, what could you do? You could synchronize. Yeah, that's a good idea, right? If you want to keep throughput. Or you would have had to invent your own queue. Well, you might as well use akka. So that's kind of cool, right? So what do we get from this? Well, we get a list of images. So given big image, pull out the faces. Okay, nice and easy. And then for each face, it's the same job, identify. Now, the identify code, if you look at it, that looks almost exactly like the code we've seen a moment ago for the scene classification. Because it uses the same library, right? The only thing that's different is the shape of the network. So where I've used AlexNet for the scene recognition, this is a deep face variant of AlexNet. So it's a slightly shallower network, it has slightly different shape. You can see that the images that are coming in are smaller. So whereas for the scene classification we had 100 by 100 pixels by 3 colors, where say faces are kind of small, right? So we're going to do 50 pixels by 50 pixels by 3 colors. That's still a lot of pixels, right? 50 times 50, that's a lot. Times 3 is even more. And so we treat that as a row vector and we apply it down to the whole network. Okay, but the code is fairly simple, right? If we pass some threshold, we return back that it's an identified face. If it isn't, right, so if we identified a face, then sure, the face that we're holding, that's someone we know. If it isn't, then, well, it's an unknown face. Right? It is a face, just don't know who it is, which will be the case for most of us. Which is kind of cool, right? No one knows who we are. Excellent in this world. Okay, what do we do? Well, we prepare an envelope, we send it back, and we return these futures. That's really simple. Okay. Yeah, now what? All right. Let's try this first. Let's deal with our persistence. So remember what I said about this sort of like almost two-phase persistence. We received a message from Kafka, And then we call persist. Now, you might say, oh, persist, 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 but there is also persist async. Doesn't it mean that I could move this down? No, it doesn't. It's not a trick, right? It's important to remember that everything in Akka is asynchronous. So even though this doesn't say async, it is actually async. And if anyone dares look at the documentation, yeah, I know. It begins with the word asynchronously. So I'm not making it up. It really is asynchronous. And so the confirmation to Kafka has to happen inside the block that's called when we receive confirmation back from the journal, saying, yes, we have written it. And then we use Akka's at least once delivery, which will generate delivery ID as this monotonously increasing watermark. And then we say, okay, well, given this delivery ID, what should be written to the journal at delivery ID? And we're going to write this tuple of delivery ID and the result. Nice and easy, which is going to get delivered to us, right? We're going to send a message to self.path, and that's going to come back here into a receive command. It's none of these messages, but it will have to be one of these messages, like so. So when we get the delivery ID that we got generated a few lines underneath, right? So this was generated here, Akka generated it. It's continuously increasing, keeps this watermark. In case it crashes, it needs to know where to replay the stuff from. Okay, well, so we get that. We call our identify and send, which is going to extract the faces from the image. Now, this is where it's long-winded. So it uses a higher cascade, which is a particular way of finding a pattern in an image. And it does so by scanning every pixel, right? It goes row by row, everything, and it hits the corner of my eyebrow. And then it says, okay, well, if I move next, I expect a certain change in intensity and color of the pixels. And it says, oh, okay, well, that's kind of good. That looks like a corner of the eye. And so it cascades down, it expands what it's looking for. And in the end, you come up with a rectangle that binds the face. But that takes a long time. Every time we send an image that might contain a face, if I send an image of this, it's quick, right? Because clearly none of this matches this pattern. Really nice and easy. But if I send an image that might contain a face, and a great example of that is this one. Oh no, actually, sorry, not this beer. This doesn't contain a face for sure, but this one does. Well, at least the computer thinks it does. This one. See, this gets identified as face. Well, kind of right? It sort of is a face, not really a human, but hey-ho. We know, computer doesn't. And so this image takes much longer to process because the cascade kicks in and we have to do loads of computation. And so we wouldn't be able to reply back to Kafka with confirmation, which is why we do all of this complicated double persistence that you've seen here. Now anyway, once we've successfully processed the images, we can confirm delivery to us. Remember, this is our local journal. So we've already confirmed to Kafka. That's happy. And we have now processed the message ourselves. We have sent a response the way we expect. And so the last thing we have to do is say, we're good. Let's confirm it. So that if we now crash, we don't get this message redelivered to us from the local Akka journal. This is slightly different, right? When we get this message from the journal, it's because we crashed here. So what do we do? Why did we crash? Who knows, right? Like I said, maybe the producer failed. Maybe something else has gone wrong. And so we deal with the on failure case. So if we crash, it's like if we crash again, we really want to make sure that the supervision mechanism kicks in, that it's not hidden. And so we send self the kill message, which then triggers this supervision strategy, and we're all smiling. Okay, wow, well, yeah, we'd better be smiling because it's 2:54. All right, last one, I promise. All of this stuff, we promised that, no, actually one more. But we won't program, I promise. No, we will program. Look at that. Nice and easy. Like so. You know, fire at most once delivery. So it's the same pattern, right? We receive a message from Kafka, except we just put it on this context, so local actor event stream, and we wash our hands off the whole thing. Never mind, you know. It goes into a web page with some WebSocket. If we lose one, we lose one. None of this makes any difference. Okay. Finally, the WebSocket. All right, all right. Okay, well, that's nice and easy. So when we get a request to dashboard, we talk to Akka streams. That's going to handle all the upgrades of connections. So it's going to reply back saying, what is it, HTTP 100 upgrade? Yeah, something like that, right? It's going to say, oh, upgrade, we're switching protocols, we're going over to WebSocket, and then we're going to keep feeding this WebSocket from this source, which is giving us these summary objects which contain top handle summaries, which are going to be displayed. I won't bore you with HTML, but you know, I mean, this is JavaScript, right? Would you imagine? With like XML. Yeah. Anyway, let's all write Scala. Okay, well, I think we're good, right? This is looking reasonable. Everything looks like it's going to work. So what do we need? Let's start a few components around it. So we're going to start the CK of the SMAC stack, you know, the Cassandra and Kafka. So let's do that. Of course, if I did SBT Docker, you know, we would have been able to build the entire thing and provision all of that, but it would have to download all these images from S3, and they're about 90 megabytes, and you know, I really don't want to push the Wi-Fi. It'll be bad enough to get stuff from Twitter. Okay. It's going to get started. We have our Akka. We have our Kafka. We have Cassandra for the persistence. Okay, this is looking good. All right, how about it? So yeah, ready to go. Okay, now let's start it. So we have, just to measure, right? We have this. We have the ingestion component with fire and forget delivery. We have a Kafka topic where the envelopes go. The envelope has a payload that contains the image bytes. We have two consumer groups. Each of these consumer groups will do guaranteed at least once delivery. The one above is going to do it in a slightly dumber way because it can confirm immediately because we can do really quick processing. The one below is more complicated because it needs to do local persistence and at least once delivery within the journal. So we like read stuff from a distributed journal, write to another distributed journal, but we are only doing that because we really cannot lose a message. And then we're going to send the messages on the scene topic and the identity topic, which is going to get consumed by the dashboard service, which doesn't really care. It's going to go do at most once delivery. Right. Now, where do we have it? Excellent. Okay. No, come on. There we go. So this will all work. We're going to do it in this horrible way, define the data points, and let's go. Get it compiling. Okay, I haven't made a mistake. That's encouraging. So this all starts up. I'm going to carefully take my phone, and you might want to do the same thing. Now, I have stashed away a picture of salad and beer and cake so I can cheat. But if any one of you want to take a picture of any old anything, right, that's the fun bit. What we're going to do, so hang on, this is the thing. So this seems to be good, right? We've started everything, okay. Let's get our dashboard going. Could not be found, okay, this is dangerous. Okay, right. Let me be the first tweet, but then knock yourselves out, right? So I'm going to say, hello. I'll take a picture of this room. It's going to get it so wrong. It'll be, you know, great. All right, smile. So I have local salads. I'm sure you'll be salads. All right. Hello with Reactive Summit as a tweet handle. All right. Let's go. So if the internet and demo gods are in favor, we should. Oh. Okay, you were cake. That's good enough. And there was a face in there somewhere that matched Helena. So give it a try, right? That was me. But if any one of you want to give this a go, take a picture of any old anything, hashtag Reactive Summit, and let's see what it does. Yeah, I mean, I should have probably got the scene recognition to actually... Oh, there we go. Wow. Okay. Anyone else? We can handle about 40 megabytes per second, so, really go for it. On this machine. So let's see if we can break it. The only thing that it doesn't survive is sleep. When I close the lid and open the lid again, wow, that's it. The whole thing crashes. But, we don't do that in AWS. All right. Now we're going. Okay, fantastic. Oh, keep tweeting. Any questions? Okay, stunned silence. I'll give you one. Here's the code. Clone all of this. You can SBT Docker it and build everything. The images are there. It's a slightly longer website. I'll tweet it again properly. We have two models, one for identity, one for scene, and each of these models has 3 files: config, labels, and params. Config is the shape and the architecture of the network. Labels is the human-readable text for the labels, and params are these floating point numbers that make up the parameters of the model that I've trained. In this source code, I've included all the training programs. So if you want to knock yourself out and run the training program overnight and make it recognize different things, you're more than welcome to it. Just to give you an idea, and this is quite cool, Jonas is going to kill me, but it is fun. So the faces, right, just to give you an idea of how it all shaped up. Oh, no, it's not on this machine. Anyway, never mind. I have some horrible pictures. What I've done is, quite simply, images Google.com, right, and there were some good ones. This is not him for some reason. There was one at various talks where he looked very angry, and there were some other ones that were clearly not Jonas, which are not appropriate at all. But you're all tweeting, so that's all good. Thanks for your attention, and enjoy the conference.